I'm Dr. Mark Biesinger. I'm the Director of Surface Science Western, Canada's leading surface analysis and materials characterization facility. We're located here at the Discovery Research Park at Western University in London, Ontario, Canada. Every year we work with hundreds of companies from across North America, helping them solve their surface and materials related issues. Today you're going to meet some of our scientists, see some of the state-of-the-art instrumentation that we have, and they'll talk to you about some of the work they do with industry.
My name is Talia Standish, and I'm a research scientist here at Surface Science Western. Here we have our Raman spectrometer, and Raman spectroscopy uses lasers to probe materials and the molecular bonds that are in materials to characterize things like different types of carbon bonds, oxides, polymers, and a variety of other kinds of material.
Hi, I'm Becky Sarazin, and I'm the polymer expert at Surface Science Western. This is our FTIR instrument. It analyzes polymers, organic materials. This is an example of one of our samples. It's a polyethylene pipe, and it has fractured. And so we will analyze samples like this, and on the computer it will come up with a match to the polymer itself, a polyethylene, and if it's oxidized or any other inorganic material that might be there that caused the fracture.
Hi, I'm Carolyn Hills-Vela, and I'm a geoscientist here at Surface Science Western. My specialty is mineralogy and mineral processing. I'm standing beside our time-of-flight secondary ion mass spectrometer, or TOPSIMS instrument. With this, an ion beam bombards the surface layer of a sample. Generated ions fly through the flight tube at different speeds and arrive at the detector or mass spectrometer at different times, hence time-of-flight mass spectrometry. This instrument is very surface sensitive and is particularly good at identifying organic molecules. As well, it's got imaging capabilities to provide a spatial distribution of species on your sample, which is really good for materials failure analysis. For mineral services that we provide, one of the things is a TOPSIMS surface analysis. With this, a comparative analysis is done between the surface chemical species on mineral grains in flotation samples, and this is to determine whether surface chemical species are affecting the flotation performance of the mineral grains.
Hi, my name is Talia Standish, and I'm a research scientist here at Surface Science Western. Thermogravimetric analysis, or TGA, is a technique that uses heating to characterize materials. This is our TGA instrument, and here's the furnace where the sample goes in, and then the furnace heats up, and as it heats we see mass loss, which then tells us about the compositional characteristics of the material.
Hi, my name is Han-Yong Nie. I use two types of instruments. One of them is time-of-flight secondary ion mass spectrometry, which is used to investigate surface chemistry. Another one is atomic force microscope, which is a mechanical probe microscope. Surface morphology is mapped by scanning a very sharp tip across the surface under a preset interactive force as the feedback parameter. Due to the very small tip used in atomic force AFM, we got a surface morphology at the nanometer scales. For example, if you have a very smooth surface, this is the technique of choice to quantify a surface morphology. In addition to surface morphology, AFM can also be used to probe surface mechanical properties of the surface. For example, I have used this approach to investigate the dispersion of additives in polymer matrix for composite polymers.
Hi, my name is Heather Bloomfield, and this is the Scanning Electron Microscope coupled with Energy Dispersive X-ray Spectroscopy. We use the SEM to look at surfaces of samples, and coupled with EDX, we can detect the elements that are present at the surface. I typically work a lot with automotive companies looking at paint defects and helping them solve their coating issues.
Hi, my name is Tom Dim. I'm a research scientist in Surface Science Western, and I am part of the mineralogical group that provides service to the mining industry. The so-called dynamic SIMS technology can provide a very sensitive trace element analysis with a detection limit in the range of 100 to 200 particles per billion. And we have two generations of dynamic SIMS instrumentation. Over there is the old Chemicus SIMS 3F instrument, and this is the new generation Chemicus 6F instrument. Both instruments use highly energetic ion beams that are used to analyze solid-state samples. How it works? The primary ion beam is focused on the sample surface. It will remove small amount of material that is ionized, and these secondary ions carry information about the sample. They're detected in a magnetic mass spectrometer. When we raster the primary ion beam across the sample surface, we can remove layer after layer and can measure and quantify distribution of trace elements in these depth profiles. We use this instrumentation to provide essential service to the mining industry, and I'll give you two short examples how we do that. The first example is a mining company can develop new gold deposits. So they need information: what is the gold, what kinds of formal gold is present in this ore deposit, and in this case we analyze their sample, and we actually using dynamic SIMS instrument we can actually quantify very accurately the gold concentration in different mineral phases. So having this detailed information, the mining company can design a proper technological process for optimum extraction of the gold. Another example, we very often work with the operating gold processing facility. So typically, a commercial gold deposit has about 2-3 grams gold per ton material. And to be profitable, the mining producer has to at least achieve 80% efficiency of the gold extraction. But very often, for different reasons, this target line is not met. So they have certain losses and they'll come to us for help. What we can do in this case, they'll send a sample from different processing products. We analyze this sample, we find where is the lost gold, and eventually identify the mechanism that related to these losses. With this feedback, we can help the company to go back on track and recover their gold recovery process at optimum condition. So this is what I want to mention. Thank you for your attention.
This is the Scanning Auger Nanoprobe. It's kind of like a scanning electron microscope, except with a scanning electron microscope, you analyze the outer few microns of the surface, whereas this is analyzing the outer few nanometers of the surface. That's good for things like corrosion chemistry, looking for stains on a surface, or any other thin film that you might find on the surface. You can also do depth profiling with this machine using an argon ion beam. So you sputter away material, analyze, sputter, as you drill a hole down into the material.
Hi, my name is Brad Colby. I'm a research scientist here at Surface Science Western. My background is in materials engineering. One of the techniques that I do is scanning electron microscopy. The instrument you see here is an ultra-high resolution field emission scanning electron microscope. This machine allows us to see features on the order of nanometers. So incredibly small features, which has applications in nanotechnology, coatings. The other aspect of SEM is it gives us elemental information as well. So we can see surface morphology, but we can also see what elements are composed of the sample.
Hi, I'm Lindsay. I'm a graduate student at Western University, and I study corrosion through the lens of electrochemistry. So I'm looking at the corrosion behavior of the metallic container that'll be used to store used nuclear fuel in the Deep Geologic Repository. So I use this electrochemical cell in order to expose those materials to the chemical species that we expect to be present in the repository. And so I'm able to use electrochemistry to get an idea of those reactions, those chemical reactions that are happening at the metallic surface that are causing the corrosion, and also get an idea of the corrosion rate, and I'm able to do this in this electrochemical cell. They come in all shapes and sizes, but here I have my test sample mounted in the bottom. In the body of the cell, I'm able to control the conditions that I'm exposing my sample to. I also have certain other features like a reference electrode that gives me a stable and meaningful reading. And I'm able to also feed gas into my cell to control the conditions that I'm exposing my sample to. So all of this research is basically going towards being able to predict whether that used nuclear fuel container will stand up to the standards that we need for the safe disposal of used nuclear fuel. And we want to be able to predict its service lifetime, which we hope to be on the order of about 1 million years.
Hi, my name is Dr. Vahid Dehnavi. I'm a research scientist here at Surface Science Western, and this is our X-ray diffractometer, or XRD for short. XRD is primarily used to characterize materials, mainly crystalline materials. Let me show you what it is composed of. The XRD is mainly composed of 3 different parts. We have an X-ray source here on the left, we have a sample holder, and we have a detector. So the X-ray hits the sample, and the diffracted X-rays are collected by the detector and then analyzed. This machine is capable of telling us what kind of materials we have. So basically, we can identify the phases. We can also measure the residual stress in a sample, and we can also analyze thin films and coatings with this machine. We have used it for quite different kind of projects, different industrial clients. We've used it for failure analysis of samples. We analyze corrosion products, and we use it like as a method to help different industries identify their products.
Hey there, my name is Ivan Barker, and what I'm standing in front of is a microcomputer tomography system, or micro-CT for short. This instrument kind of works like a X-ray 3D scanner. It lets you look inside things using X-rays. So what I have here right now are some cement blocks, and using the micro-CT, we can actually make up a 3D model of the internals of these cement blocks, which is kind of cool. It's a non-destructive technique, which means we don't need to prep the samples, we don't need to cut the samples. You just throw the sample in there and we can start looking inside it. We can look at big samples, as you can see, but we can also go down to about 1 micron or so in resolution. So it's a really handy instrument. It works on density differences, so it's good for looking at, let's say, porosity in rocks. If you are from oil and gas industry, that might be interesting for you. But you might also be looking at cracks or corrosion in, let's say, copper pipes. And just, it lets you look at the kind of distribution of these things in 3D, which is great. The different components we have here is we have an X-ray source here, and we have our X-ray detector on this side. What it does is it shoots the X-rays out, the X-rays pass through the sample, and they're received by the detector. The sample then kind of spins 360 degrees, and we get a series of projections on the detector itself. It works basically like you're getting an X-ray of your hand, and you rotate it, rotate it, rotate it. Then you mash all those X-rays together and you get a 3D model. And then we can analyze that afterwards, get some cool pictures, get some really neat movies, and we can also get statistical analysis of our density differences, like interconnected porosity, things like that. So really cool instrument, easy to load up. Data is really easy to visualize because it's movies and pictures and stuff like that. But it's also very powerful because it allows us to do statistical analysis in 3D, which is really awesome.
My name is Han Yong Ye. This is our KLA 10-core surface profilometer. This is a lot more similar to what we have for AFM, but with a much larger tip. It can handle a much larger area and a much higher height range. So here at Surface Science Western, with both AFM and this profile, we can handle areas from the nanometer scale to tens of centimeter scales.
This instrument is an X-ray photoelectron spectrometer, or XPS. You shine X-rays at the surface of a material and photoelectrons are produced. And those photoelectrons, we can measure their kinetic energy. And that tells us information about what elements are present at the surface and their chemical state. So by chemical state, I mean you can tell whether you have a silicone versus silica, chromium-3 versus chromium-6, which is the toxic form of chromium, those sorts of things. The information comes from the outer 3 to 5 to 10 nanometers of the surface, and so it's a very surface-sensitive technique. And XPS is one of the techniques that Surface Science Western is known internationally for. We have a lot of expertise in this area.
My name is Talia Standish, and I'm a research scientist here at Surface Science Western. This is our differential scanning calorimeter, or DSC, and it's used to identify and characterize materials based on their physical and chemical changes as they're heated.
For further information, please visit our website at www.surfacesciencewestern.com.